Hey guys, I just wanted to record a quick video about this is going back to um, the group of upper triangular matrices like this. So you have n by n matrices, ones along the diagonal, zeros below, and arbitrary entries above, like whatever elements of the field you want. And I want to show you why these satisfy the definition of being a nilpotent group. Okay. Um, so let's prove that. First, associated to this group, we have a bunch of nilpotent matrices. You know? So I'll just define them. We have this, these aren't groups, but we have this set N, which is zeros on the diagonal, zeros below the diagonal, and anything above. Okay, and we'll call G1 just to be the identity plus elements of N. Right? So this is all of G. G1 is all of G. And then we can take things in N, like we can look at N squared. Okay. Elements of N squared are just something in N times something else in N, and add them up in all possible ways. Okay. But anyways, it turns out what you get is the set of n by n matrices where the diagonal is 0 and the entries right above the diagonal are 0 and anything else is above here. Okay? And we'll let G2 to be the identity plus n squared. Okay? Those are the matrices with 1 on the diagonal, 0s directly above the diagonal, and anything else goes above that. Okay? And then n cubed is going to have zeros on the diagonal, zeros above the diagonal, zeros above that, and then arbitrary, whatever entries you want above that. You know? And eventually you get to n to the power n minus 1. Well, there's just like some scalar in the top right hand corner and zeros everywhere else. Okay, and we'll let Gn minus 1 be the identity matrix plus matrices whose top right corner is possibly non-zero, but everything else is 0. And then Gn is I, the identity matrix plus n to the power n, and things in n, when you raise them to the power n, you get 0. So this is just the trivial group. Okay. And now we want to show that this sequence of subgroups of G gives you a central series. Okay, so let's see what we should do. Okay. So we have to prove that, G1 mod G2 is contained in the center of G mod G2. G2 mod G3 is contained in the center of G mod G3. And all the way down to Gn minus 1 it has to be contained in the center of G. Okay? Gn is trivial, so that's what the last statement is saying. Okay? And if we do that, then we'll have shown that these G's, G1 down to Gn, form a central series for the group of upper triangular matrices with ones on the diagonal. Okay. So first, let's do like some basic properties of G. We want to compute the inverse of an element of G. Well, if we want to do I plus R inverse, well, it's actually, you might guess it's like given by like a geometric series, and that would be false if you had to use it would possibly be false if you had to use an infinite geometric series. But just notice, since r to the n is 0, this kind of truncated geometric series is actually the inverse. Okay, so you can check, like, multiply this times 1 plus r, and you get 0. Okay. So this is, this series is 1 plus r inverse. Right, so we can compute inverses of things in G. And notice that if we want to compute whether or not Gj mod Gj plus 1 is contained in the center of G mod Gj plus 1, well, we just need to compute whether or not the commutator of an element of Gj with an element of G is contained in Gj plus 1. Because if it is, then when you mod out by Gj plus 1, you get that everything in Gj mod Gj plus 1 commutes with everything in G mod Gj plus 1, which is just saying that this is in the center of this. Okay. So now we're going to take something in Gj, we're going to take something in G, compute its commutator, and we'll work, like, when we work, we'll ignore anything that is in n to the j plus 1. Yeah. I guess it's kind of cheating just jumping to that. But we're trying to work modulo, like we're thinking of, like, we want to see if the result we get is in Gj plus 1. So things in Gj plus 1 have, like, our identity plus n to the j plus 1. So we're kind of ignoring that. And, you know, the reason is that we want to end up in Gj plus 1, so things already in Gj plus 1 kind of we don't care about. Okay. Alright, so with that in mind, we make this computation. We do the commutator of I plus r with I plus s. So you do first thing times second thing times first thing inverse times second thing inverse. But the reason why I write the inverse of I plus r as I minus r is because that is the inverse up to this, like, more powers of r, but r squared is in n to the j plus 1. I'm ignoring everything that's in n to the j plus 1. So here there should be plus r squared minus r cubed and so on, but I'm ignoring all higher powers. Okay. So I just have I plus r times I plus s times I minus r times this whole thing. Okay, so first let's just compute I plus r times I plus s. We get I plus r plus s plus rs. But r is in n and s is in n to the j, so rs is in n to the j plus 1. So we're ignoring anything in n to the j plus 1, so we can ignore rs. So now we have I plus r plus s times I minus r. So we get I plus r plus s, minus r squared minus sr. Okay, sr and minus r squared we can both ignore because those are in n to the j plus 1. And so we're left with I plus r minus r plus s. So I plus s. Okay, and then this is just I plus s inverse, and I plus s times I plus s inverse is the identity. Okay, so we've shown that ignoring anything in I to the j plus 1 or higher, we've shown that I plus r like commutator of I plus r with I plus s is the identity. So this is all mod n to the j plus 1, and that establishes our condition up here. that commutator of Gj with G is contained in Gj plus 1, and therefore, since it's true for all J, we have a central series. So we have G equals G1 contained in G2 contained in Gn. This is a central series. For G. Okay. And so we see like nilpotent matrices give us our example of, well, one of our first examples of nilpotent groups. The other example being P groups. In particular, like if the field was the real numbers, this would be an example of an infinite nilpotent group. Okay. Sorry for the rather long video. Thanks for watching.